So now let's look at how to implement semantics using MPS, right? So for this, we will implement, as I mentioned before, there are two different ways, or at least two different ways you can implement semantics for your language, right? So you can create a generator which generates language, your generates code into a target language, which is then essentially defining the semantics of your language. The other way is interpreter, right? So we have two languages now, the state machine language and the state machine test language. For both of them, let's go ahead and build a generator for the state machine language and an interpreter for the state machine test language, right? Okay, so let's begin with the generator. We already built our state machine language, which looks something like this. And for the sake of this session, we will generate a code for state machine, which which has a current state variable, which tracks what is the current accepted state. It's initialized to the initial state from your language. And then there is a trigger function, which essentially takes your event as input. And depending on what the current state is, it moves it to an appropriate state based on what the input is provided, right? So let's go ahead and let's build our generator, right? So in order to build our generator, as just like with the structure, editor, and so on and so forth, we have a generator aspect, right? Let's begin with our state machine language, right? So here, there are like 1,000 different kinds of generation logic you can do, but we want to now map our state machine into a Java code, right? So for that, we will use the root mapping rules. You can also use reduction rules to directly map each concept in your language into a model in whatever language you want to, right? So let's map our state machine to, let's give it a name, to Java code, right? Go ahead and create a root template. I want it to be a class, right? And MPS has created a class, which is essentially a template. Now, what is a template? A template is essentially a model in some other language which has certain meta variables that can be bound to values from your input, right? So the idea here is meta programming, right? You have some static part of your code, which is like this. So right now, if this is my generator, right? And then I have just, I don't know, uh, this would, now I actually have a generator for my code, right? If I go to my state machine, and I say, hey, okay, there is already an issue here. Let's create an initial state. Let's make it happy. Let me preview the generated text. Voila, it's just going to print out whatever I had, right? But we don't want any Java code. We want a Java code that is somehow influenced by our state machine. We want to generate variables for each states and each event, and we want to create a current state variable which is initialized to the initial state, right? So let's see how to do that. Let me remove this dummy function. So as I mentioned to you before, just now, MPS templates use the concept of meta variables to bind values to individual elements from your input program. So for the way you build it is you simply write Java code the way it must look like, or in this case, Java code, you can write code in any language that you have inside MPS. And then you try to bind each sections of your code that needs to be dynamically generated based on your input, right? So for example, here, we need to generate one declaration for each state and each event, right? Okay, so first let's create a dummy declaration for our states. Private, was it? Yep, final int, let's give it a dummy name and a dummy value, right? Now, we want this code to be generated for each state in our state machine, right? So we will go ahead and bind this with a loop, right? We want to loop through the node's contents, not any contents. We want to loop through the states, right? And oops, there is a problem here. I have bound everything, not just. Okay, now node.contents, but node.states, node.all contents. I just wanted to state. Now I want the state to have the state variable to be bound to the name of the state that I'm currently iterating over. So here I can add a property macro. So this is a second kind of macro. As I mentioned before, MPS uses the concept of meta programming, and with meta programming, you essentially have macros or meta variables which are then bound dynamically to values from your input program, right? So I'm going to add a property macro, and this property is going to be simply node.name, right? And here the node is of type, or node is of kind state, because we are looping only through states. So MPS kind of knows, and it's only going to display the properties or children of that particular kind of node. And the value here, it can be anything unique, right? So let's this is also a property macro. It's going to be node dot name dot hashcode, right? And we can simply copy this over to create such declarations for events, right? And now we're going to loop through events, and I think everything pretty much can remain the same because event also has a name. Let's now rebuild this and see how our generation looks like. If everything works fine, I should have 1, 2, 3, 4, 5 declarations, 2 of them states, and 3 of them events. Beautiful. Okay, now let's go ahead and create a current state. All right. That's going to be, again, another declaration, but I don't have to loop over anything. It has to just be one current state, which points to the initial state, right? Yes, current state equals whatever dummy value, right? Now the dummy value is going to be my initial state. So I need to have a property macro, and this is going to be dot. So now the node is state machine, right? So we are not looping over anything. So the context here is still state machine. So I need to find out all the states where initial, I can't say where because there could be more than one. So let me just find first, and I'm going to assume that the constraint checker has, or the type system has taken care that there is only one initial state, and then we have its name. Reload. I go back. I have a problem here. What is it? I am expecting an integer. Hmm. Current state has to be an integer. Yes. So we need to refer. Okay, this is why you introduce, I want to introduce another kind of macro called reference macro, right? So our current state has to refer to an existing state that was already generated, right? So if you want to refer to nodes that are in the middle of your generation process or something that is part of your generated code, you use what is called a reference macro, right? So uh, delete this private int current state, state, right? It's not any state. It's going to refer to node dot states dot find first initial dot name. Now it should be happy. Yes, and if I go ahead and redo my state machine, preview generated text. Voila, it's pointing to state 2, and I hope state 2 is our initial state, right? So let's try to change it and see if our generation process still refers to the correct node. Yes, perfect. Now we go ahead and generate our trigger function, right? So our trigger function is a public void. It returns nothing. It's a trigger function. It takes as input some event, right? Now, I need to switch through the current state, right? Depending on what the current state is. But I need to have a switch for each I need to have a case for each statement, and inside the state, or not statement, each state, and if the current state is, I don't know, state one, depending on the transitions available, I need to check the trigger of each transition with the event input that is provided, or sorry, the trigger of each transition with the EVT input that is provided, and then depending on that, I change the current state to the appropriate target of that transition. Right? So let's go ahead and do it. As usual, let's type in some template code which we will bind. So case state, it can be any some state now, right? And block statement. If so, this also needs to be looped around for each trigger of your valid transitions, right? And then current state is updated with, let's keep it like this. We're going to bind it anyway. So first things first, let's bind these guys to loop around the states, all available states, right? And then this guy is now bound to that particular state that we are operating on. I need a property macro here or a reference macro. So I need a reference macro. Now the context is states, so I need to just say node.name, right? And then the event, right? So this guy needs to loop over every available transition, right? And then the event is bound to the transitions target, node.trigger, and then this guy is bound to the target. I don't need to write any code. Yeah, I need to tell what property of it that needs to be displayed for me to make it happy. It should be fine. And I think we have our first generator, right? Yes, perfect. So for state two, you have two transitions, and based on the transition, the target state is defined by the transition itself, right? Now, of course, this is one kind of dummy generator. So the point of it here is not, of course, if you ask me if it is the right way to implement a state machine in Java, probably not, right? But the point here is not to create the perfect state machine, but to understand how you can use generators and meta variables and macros to map your language into some other language, right? So we've just seen one kind of generator, which is the model to model generator. In MPS, you can also have a model to text generator, but in our course, we are going to be generating to Java, so you will probably only always concern yourselves with the model to model generator, right? Okay, so generation, one way of defining your semantics. The other way is the interpreter, right? So as I mentioned before, interpreters are kind of a mapping of the operational semantics that you learned, where you say each concept in your language, right, is evaluated so, right? So if I have a binary expression, take the left-hand side, take the right-hand side, perform an arithmetic operation, and the result is the meaning of this expression, right? In some other bizarre language, you provide two integers. It could simply be the concatenation of the two integers. So 1 plus 2 could mean 3 in one language, 1 plus 2 could mean 12 in another language. And how do you define them? You use interpreters to essentially provide evaluators for each concept in your language. And for showing how to implement interpreters in MPS, we are going to implement an interpreter for a test language, right? Specifically, we are going to evaluate if each assertion is in the correct state, right? So let's take this state machine, this test, right? So it is for state machine one, right? The initial state is state one. So the first assert should be evaluated to true, and you're triggering event two, right? Well, you trigger event two and you go to state two, right? So this one should work. If I change it to state one, it shouldn't. So the second assert statement should be evaluated to false, right? So let's go ahead and build an interpreter, right? So before we build the interpreter, right, let's look at how to make sense of our interpreter, right? So the interpreter kind of like is going to behave like this. You run your interpreter, you create your interpreter, which is then triggered using an intention. Intentions are kind of like tool support for your language for quick fixes, refactoring, whatever, right? It's essentially like when you have Eclipse, you right click and say, hey, I want to rename this variable or something, right? Things like this. And once you have an intention which triggers the interpreter would essentially evaluate each of the assert statements to true or false. And after the evaluation has happened, it's going to communicate it in certain ways. We'll see how. Back to the editor, and the editor is going to look up the results of each assert statement and then either change the background color to blue or red, depending on whether the assert statement or was evaluated true or false, right? Okay, so in order to build all of this, we need to build an intention, we need to build editor support for it, and we need to build the interpreter, which is the main part, right? So, I mean, of course, you can still have an interpreter, that's it, and you've kind of defined your semantics. But if you want to have some visual way to express what are the results of your interpretation, you need to have some way of triggering the interpreter and communicating the results back to the editor, right? Um, for all of this, we will use a sort of cache, right? A cache is something that you pass around in the interpreter's environment, and then also is something that your editor can look up after the interpreter's completed evaluating your node, right? Okay, so in our case, we are going to have two. So essentially, cache is something you can think of like a Java object, right? Which is an intermediate representation of your existing language. So one to represent the test case, one to represent the state machine, and then the test case on top of serving as an intermediate representation for the particular node. It's also going to be able to it's also going to store within itself a map of each asserts inside your test case to Boolean, whether it's evaluated to true or false. And then you're going to have an object to represent the state machine, which is essentially going to keep track of the current state that's initially set to the initial state. And then it's going to allow you to move to new states depending on which trigger statement was called previously, right? So first things first, let's build the cache, right? So here it is. Okay, so for the sake of brevity of this video, I have skipped the parts where I just typed in the cache here, right? So essentially, as I mentioned before, there is one object which represents your state machine, which has a reference to the machine that is being operated on. It has a reference to a tracker of the current state, and then the current state is initialized to the machine's initial state. You have operations to get the current state. You have an operation to move the current state to a new state, right? And then you also need to have a kind of a key, right? So this is used used in the interpreter to keep track of the environment and which current test value or the state machine value is being operated, right? So we are never going to use the state machine value directly. We only need the test value. So the test value is what is going to have an instance of the state machine value as I have here, right? Your test value as a reference to the test case. It has a map of the assert statement to Boolean, which is what is going to be updated and what is going to be looked up by your editor later. All right, you have an operation to update the result with whatever value you have interpreted for each statement. You have an operation to get the corresponding machine, and you have an operation to check if a particular state is okay. Okay, meaning if it is evaluated to true or false, right? And this operation is what is going to be ultimately used by your editor to change the background color. Okay, now let's go ahead and build our interpreter. So for building an interpreter, the plugin that I talked about, MPS utils, which has grammar cells, also comes with the interpreter, right? So interpreters go in a solution that have to follow a very specific naming convention, right? For whatever reason, so that MPS can actually uh, look up your interpreter in your. So I don't think the solution needs to have any specific name, right? But the model has to be, so there are a couple of other constraints. Your solution has to be of type other so that your MPS class loader can pick this up, right? And then the model where has to be called plugin, right? Where the interpreter goes. Now let's go ahead and say my interpreter is going to use the interpreter language that comes with the MPS util plugin. I'm also going to be using the collections aspect of base language. Base language uh, is the Java alternative in NPS. So I'm also going to go ahead and so it has the Java base plus a bunch of extensions. One of them is collections, right? So I'm going to use them. So I'm also going to add it already here. Okay, let's go ahead and build our interpreter. New interpreter, right? So interpreters have a name. You can give it whatever name you want. State machine test. Category is kind of, it means nothing right now. Uh, there were supposed to be multiple kinds of interpreters, but currently I think arithmetic is the only thing that is supported. You don't need to specify the languages that are evaluated. That's going to come from the evaluators, right? Okay, so, and it's generally good practice to not have the same interpreter for like 20 different languages, right? So try to have one interpreter per language, or maybe multiple interpreters per language. Okay, so we need to evaluate a few things. We need to evaluate our test case. We need to evaluate our assert statement and our trigger statement, right? So our test evaluation of our test case is rather simple. You initialize the environment with the cache, and then you go ahead and call the interpreter for every content inside the test case, right? And then for the trigger statement, the interpretation is simple. You check what is the current state, and then you find out all the valid transitions from that current state, and then you just depending on whatever the event that is triggered, you just move the current state to the new state that is appropriate for that particular event and the transition and the valid transitions, right? And then for assert statement, you simply check the current state and see if the current state is equal to the state that is provided in the assert statement, and then you update the results record, right? Results map. Okay, so let's go ahead and build it. First things first, we need to make sure that our interpreter can see our test language, right? Okay, test case, and then here your interpreter is pretty much just evaluation is pretty much just base language code or Java code, right? With some extensions on like how to keep track of our environment. First, let's initialize our cache and then tell our environment that this is the particular test case that we are operating on, right? So we need to create the state machine value. I need to import it. Equal to new machine, oh sorry, SM value, and then this is going to be, the node currently is the test case, so it's going to be the for part of this state machine. And then using that, we create our test value. This new test value, it's going to be this machine and then the node, right? That's it now. And then we update our environment with the. And then if you remember, I talked about the key, which has to be a node of type-based concept, right? So, okay, for this key, the value is test, right? So this is the guy, this is this test object that we are going to update and pass around, right? Like a football. So now the interpretation for test case is rather simple. You just say for each content C in node dot contents, right? Just ignore because you don't need to do anything with I think this is also a bug because you need to assign the value to something, right? It's also a bug with the interpreter. And then you're going to say this hash kind of says, hey, just invoke the interpreter of this content, whatever it is. If it's an assert statement, go ahead and invoke the interpreter for the assert case with this C object, right? Or if it's a trigger, do the same thing. I have to return the test because once the interpreter is triggered with your intention, I need to get this value and then use that to modify the editor, right? Okay, so let's go ahead and define the interpreter for trigger. It's rather simple. First things first, we need to get our object from from the environment. So environment is just a map, right? A key value map. We got the value now. Okay, we need to cast it. We know it's a test value. Okay, and then first thing is we need to get all the current state, whatever that is, and then in the first statement, of course, it's going to be probably the initial state, hopefully, right? You could have written an assert with the non-initial state first. Okay, so let's try to find out what is the current state, what is the transitions from there, what are the valid transitions from there, and then let's try to find out what are all the event states that it can move to based on the event that is provided here, right? So first thing, so we are looking for a sequence of transitions. Okay, I need yes, right, valid transitions equals node dot states. Oops, no, I'm working on a trigger, right? So a trigger statement has an event. So I first need to go up, find my test case, find the state machine that I'm working on, right? And then now I need to find out the states where, huh, yes, I don't need to do all of this jumping around, right? I have my machine within my test, so I can get that. I machine dot current state, get the current state from there, and then get the transitions where, so the trigger of the transition is equal to the target of the current node, which would be, oh, it's called something else, the event that is triggered, right? So the trigger of the transition, so I've got all the transitions where the trigger of that transitions from the current state matches my whatever triggers event, right? Now I've got it. Now, of course, in an ideal scenario, this shouldn't be a sequence. I should have only one transition, but we didn't build our language in a way that we prevented by design, right? So you have only you have only one transition per trigger event. So we'll keep the semantics as for each we are just going to go through all of the valid transitions and then just move our state for each of them. So it would just simply be the last transition, right? So I'm going to update my cache with the new state. I'm just going to say d dot. It's going to be the target. That's it. Now this is my interpreter for the trigger. Now let me also finalize my interpreter by building an evaluator for the assert concept. This is again rather simple. I can copy over this guy. I first get my test from the cache, right? And then I say, and then now I just need to first see if I am in an appropriate state, right? If my assert state is actually the current state, right? Current state equals node dot target or state, right? And then after I've done this, I need to update my cache. I need to say this dot update result. Okay, node is okay. And then I return is okay because this is also going to be used by our intention and editor later. And we've kind of now done with our interpreter, right? We only need to connect it with our the intention and editor. So first, let's go ahead and build an actual intention that would trigger the interpreter, right? So for intention, you have an aspect called intention aspect. Okay, I can't see it here because I've already created an intention aspect. So I go ahead and create an intention, whatever, call it something, trigger test. We already used trigger, so let's call it invoke test, right? And you should say where this intention should be displayed and also what concept it is for, right? So this is for test case. This invoke test for invoke. We can keep it more fancy. Oh, kind of lost. Ah, I actually forgot where my codes were. Invoke test node dot name plus for spaces node dot for dot name. Of course, you don't need all this. I'm just trying to show you that for the description, you can write any Java code, right? So kind of showing you how flexible MPS is. Now, inside this execute, we don't do anything right now, right? We have to trigger our interpreter, and we have to update our, we have to pass around, get the cache, the test value object that was provided as part of the evaluation, and then pass it around to our editor, right? So let's just see if we can see our uh, intention here, right? So if I go and press Alt Enter here, perfect, and I press Enter, it's not going to do anything. Okay, now let's go ahead and actually invoke our interpreter. For this, MPS Utils provides an interpreter evaluation helper, which I need to import here, right? And then helper equal to, yes, and then here I just provide the same category that I provided. Right? I've not tried it with some other category, but I don't know if it works. I just tried out. But I think arithmetic may be the only thing that is accepted right now. But also this category kind of is meaningless right now. Okay, so we've got our helper, and using the helper, we want to evaluate, or rather trigger our interpreter, all these evaluators that we coded here, I'm sorry, and then we know that we are going to get a test value object out of our interpretation. So we'll just go ahead and say, hey, I want a test value, test equal to helper dot eval, right? And then I say I want to evaluate this test case, right? But now I can cast it because I know what my interpreter is returning, right? Now that I've done it, I need to put it somewhere, so that put this test object somewhere so that my editor can pick this up, right? So for that, every node in MPS has its own kind of user object, which is essentially just a map, right? So I would say node, and this node is actually a node object, so I need to downcast it to the Java semantic level, right? The base language semantic level. So let's say put user object. I also think this kind of underscore 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 exec is some kind of expected notation, right? I tried it out with other kinds of names and kind of didn't work, right? So, but it's essentially a map. So I'm going to say exec, and then I'm going to just put this test object there, right? Now, after this, I need to do a couple of things which are essentially just refreshing my editor, which I'm going to copy paste from some other place where I've written, which is not important. I just make sure I don't import anything from that language. Yes, okay. So voila, so now our intention is complete. So the last two lines are kind of not important. You just copy it and paste it wherever you want, right? Because this is just to make sure your editor is refreshed after you've triggered the info. So after you've triggered your intention, you're going to put this user object, trigger your interpreter, get the test object, and make sure it's communicated to your editor. And after that, you need to refresh your editor, right? So these two lines of code are simply doing that. They are not relevant right now. Okay, so now we have built pretty much everything. We only need to get this user object and utilize it in our editor, right? So where should this this be used? In the assert statement, not in the test case, right? So what aspect of the assert statement should be modified based on the results of the interpretation? Essentially, the background, in our case, the background color of the assert statement, right? So I'm going to use my inspector here, where I can say the background color is, I can say something static, right? But I can also add a query here, and then it's pretty much just a Java code, right? So we don't know what we need to do here. So for that, let's program a behavior method for our assert statement that would that would pick up the value from our interpreter, right? So behavior concept, yes. And then here you define a method, right? Call it, it needs to return a color, right? Java and java.awt.color, right? And then, I don't know, get color. It takes nothing because I know the node I'm operating on. So first, let's get the value from the user object, right? So we say, we need to have test value here, visible test. So this football that we're passing around will finally find its use, right? We know we are getting a test value this time. So, but the user object is not in the assert statement, but it's actually in the test case that is an ancestor of this assert statement, right? So we first find the test case, right? And then we downcast it again. And then we say get user object underscore underscore underscore. Oh, it's a string, right? And then I can typecast this to test value, right? And let's do some corner case check, because when you start your editor and you've not triggered your interpreter, this would just simply be null and throw a null pointer exception. Let's try to avoid that, right? Now, we got the test value, and from this test value, we need to know if this particular assert statement is okay or not, right? So let's create a Boolean value. Is this guy okay, right? And then test dot, we have this operation, which, right? So your test kind of has the results of each assert statement and whether it was true or false. And then based on whether this guy is okay, we return color.green or color.red, right? I don't know what the difference is, so let me just, I hope there is no difference, but let me just use the caps lock. Variable language, okay, we have an error. Yes, we did not, we left our query for the assert statement editor open. This needs to be node dot get color. Let's clean everything up, and for the sake of being thorough, I'm just going to clean up my interpreter and my state machine language. Now, if I go back and I trigger this, yes, I'm in state one. It's correct. I want to move to, I want to trigger the event two, and I want to move to state two, right? Let's create an error. Let's try to say, for whatever reason, I want to be in state one again, and let's trigger our interpreter. Voila. So that kind of completes our session, and I hope I've got your juices flowing on using MPS. What I have introduced to you is just the tip of the iceberg, right? I hope you have a lot of fun with your journey with MPS. There's a lot of resources, and I would like to thank my ex-colleague Marcus Wolter, whose intro course, which is a more thorough version of the state machine language, is kind of the inspiration for my tutorial, which I have adopted for this course, right? I also recommend you guys go ahead and look that up. And okay, bye-bye.